Hello, everyone. I'm Olympia. Thank you for being here with me in this wonderful place called Lights Out Library, and I have a great story to tell you. I'm taking you to space tonight. Recently, we went to the Jovian system, that is to say, Jupiter and his rings and its moons. Tonight, we will go even further. We will cross the orbit of Saturn, which we have also visited, and visit the 7th and 8th planets from the Sun, Uranus and Neptune. These two are called ice giants. We will see why, and I'll tell you also about the theories, the models that explain the formation of the solar system and these planets, and the difference in size and composition and orbits. We will also take a look at their moons and dive through the atmospheres of these two planets to see what there could be inside. This is going to be a long journey. But first, I would like to take a few seconds of your time to let you know that we have a Patreon page for those of you who wish to and can support this project, get more from it, and listen ad-free on your favorite podcast app. Patreon is a platform that allows you to contribute directly to our work financially. If you join, you will gain access to various new features. For example, you will have the option to listen to all episodes with or without background sounds and receive regular bonus episodes. We already offer 5 exclusive episodes to our patrons, the last of which is about the Phantom of the Opera. In addition, you will have the capability to download all these audios and participate in selecting future topics. We also offer advanced releases and updates on upcoming episodes. We hope to see you there soon so that we can continue developing a Lights Out Library, which we thoroughly enjoy. You will find a link in the description box and pinned in the first comment under the video. As always, you do not need to watch the video to follow along. If you fall asleep and wish to resume the video later, or jump directly to a particular part of the story, timestamps are also listed in the description and pinned in the first comment, as well as links to different streaming options like Spotify, Apple Podcast, and Amazon Music, which may be better suited for you. We ask that if you can, please subscribe to the channel and click on the like button. This helps us promote the channel and eliminate advertisements as much as YouTube allows us to. But before we begin, if you wish to, you may close your eyes and allow yourself to forget about any worries as we embark on this adventure together. Now assume a comfortable position. Maybe move a little to settle. Take a long, deep, relaxing breath, and when you slowly exhale, feel your shoulders drop. Release the tension in your neck. Let your face soften and your jaw relax. Make sure your fingers are not clenched and that your legs are relaxed too. And allow the sound of my voice to guide you through this journey. And now, it's time to explore. Just think about the quietness, the peacefulness of space, and the beauty of thousands of stars. You are pretty safe on this journey. So, how far are Uranus and Neptune from us on Earth? You remember from our previous space stories that there is a unit that is useful to figure out distances in space, the astronomical unit. It was defined roughly as the equivalent of the distance from the Sun to the Earth. which is about 150 million kilometers, or 93 million miles. Light takes about 8 minutes to travel this distance, and the astronomical unit is convenient to compare distances between the orbits of the planets. So the Sun to Earth distance is 1 astronomical unit. The Sun to Mars is 1.5 units. Jupiter, which is the 5th planet from the Sun, is at a bit more than 5 astronomical units. Saturn, the 6th planet, is almost twice as far as Jupiter, 9.5 astronomical units. But to reach Uranus, we need to double that distance again, about 19 astronomical units. 19 is like the middle point because the orbit is not a perfect circle. It is slightly elliptical. At its closest, the distance is a bit more than 18 astronomical units, and at its farthest, a bit more than 20. But a good order of magnitude to bear in mind is that Uranus is 19 times farther from the Sun and Earth, and Neptune is 30 times farther. At this distance, light and heat from the Sun take more time to reach them, and there is much less. They don't have a solid, rocky surface, as you know, so we cannot really say that they have a cold surface. But the upper layers of these planets are extraordinarily cold. We will see how cold when we approach them. The first close images we got from Uranus are not very old. They were taken by a probe, Voyager 2, in 1986, and they reveal the planets that look almost featureless, without the kind of cloud bands and storms that are observed on other giant gas planets. Neptune looks more animated, but both planets have conditions in their upper layers that are some of the most extreme in the solar system. So first, let's talk about what they are made of and why they are called ice giants. Until the 1940s, astronomers distinguished 2 main types of planets in the solar system: the rocky ones with solid surfaces like Mercury, Venus, Earth, and Mars, and the gas planets, which are bigger and do not have a clearly defined surface because they are made of gas in various layers, denser and denser as you move towards the center. And their core is believed to be made of rock and metal, around which gas has accumulated and remains kept together by gravitation. There were 4 gas planets: Jupiter, Saturn, Uranus, and Neptune. It was assumed that their composition was more or less similar, mainly hydrogen and helium. The 2 most abundant elements in the solar system, and most probably in the entire universe in general. They are the simplest, the smallest types of atoms. There are heavier elements, dozens of them, including some that are also relatively abundant, like oxygen, iron, and carbon. But it is believed that these elements are mostly younger than hydrogen. Like other heavier atoms, they would tend to form in stars when they approach the end of their lives. You know that the fuel of stars is hydrogen. Inside them, hydrogen is exposed to such extreme conditions that fusion happens. Atom cores combine to form heavier atoms, mainly helium, for most of the star's life. But when the end of the star nears, because it has consumed a large part of its hydrogen reserves, which takes hundreds of millions of years, billions of years, in the case of a star like the Sun, the star starts consuming helium, and heavier elements are formed. It is believed that this is how these heavy elements appear, all the way to big atoms with dozens of particles like gold or uranium. And then, when the star dies, it becomes gigantic. It explodes in a supernova, which would disperse these elements, and they will become available to form new systems. Our system is much younger than the estimated age of the universe. So, if these theories about the universe, stars, and the formation of a star system are accurate, it is not surprising that these heavier atoms are actually present in our solar system, either alone or combined with other compounds like ammonia, carbon dioxide, sulfur dioxide, or water. But still, most of the solar system, if we take into account the sun itself and all the planets, is still mostly hydrogen, and to a lesser extent helium. And as it happens, these are also the main components of gas planets like Jupiter and Saturn. They probably have rocks and metals in their core, and they have other compounds in smaller quantities in their various layers, but this isn't much in proportion. So, until about the 1940s, it was assumed that Uranus and Neptune, because they were giant planets with no defined surfaces like Jupiter and Saturn, had a similar composition. To put figures on this, it is estimated that Jupiter and Saturn are more than 90% hydrogen and helium. But it appeared through spectroscopy and estimates of their mass relative to their size, and later measurements sent by probes, that no, Uranus and Neptune were quite different in their composition, only about 20% of hydrogen and helium by mass, and a lot of compounds like water, hydrocarbons, and ammonia. These different compounds are called ices in astrophysics and planetary science. When they are independent from a larger body, like a planet, and at a sufficient distance from a star, they are generally found frozen as solids. On Earth, when we hear the term ice, we typically think about water ice. In contrast, astronomy utilizes the term ice to refer to a broad range of compounds, including water and many others. These compounds share a common trait. They freeze at or near 100 kelvins under Earth's surface pressure. One such compound is water, which freezes at 273 Kelvin, equivalent to 0 degrees Celsius. The Kelvin scale is similar to the Celsius scale, except that it commences at 0, which represents the lowest possible temperature. In contrast, the Celsius scale starts at minus 273. So water freezes at 273 Kelvin, or 0 degrees Celsius. Ammonia freezes at 195 Kelvin, which is minus 78 degrees Celsius. In comparison, methane freezes at 91 Kelvin, or minus 182 degrees Celsius. These elements make up the majority of the mass of Uranus and Neptune, which is the scientific reason why they are called ice giants. However, this term can be a bit misleading, because when we hear ice giant, we may think about a planet with a hard surface, which they are not, or one with blocks of ice floating in its atmosphere, which they also do not have. The term ice refers to the compounds they are made of, not the state they are in, because, as we will see, these compounds are no longer solid. They might have been solid when the planets formed, but they no longer are. This term was needed to differentiate these planets from gas giants like Jupiter, because their composition and formation history were quite different. The term ice giant sounded appropriate, which is why it was adopted over the past 40 years. Now, a good question is, why are some planets rocky, while others are made of hydrogen and helium, and others of ammonia, water, and methane? And why is there an apparent order in the solar system, with 4 rocky planets in the inner part of the system, then 2 gas giants made of hydrogen that happen to be the 2 largest planets, Jupiter and Saturn, and after them, 2 ice giants, which are in between rocky planets and gas giants in the terms of size and mass? To answer this, we need to discuss the theories of planet formation. One factor that makes studying the formation of planets challenging is that we only have one system at our disposal, ours, and it doesn't include that many planets. In our system, only 8 bodies are considered massive enough to be classified as planets, plus a few smaller bodies like Ceres or Pluto, which are considered dwarf planets. But overall, not that many. The starting point of a star system is relatively uncontroversial among astrophysicists at this point. Although it remains theoretical, it is backed by numerous observations concerning the chemical composition of planets, their orbits, the laws of gravitation, and even the direct and confirmed observation since 2018 of a star in formation around a newly formed star named H.L. Tauri. This star is situated 450 light-years away from us, which is considerable, but not that far on a cosmic scale. A star system is believed to form when enough matter, including gas and dust originating from a nebula, accumulates within a small space. A nebula is an immense cloud of matter floating in space, several of which exist within our galaxy. The primary force driving the formation of a star system is gravitation. Within this region of space, the suspended matter tends to form a large disk rotating on itself. An initial impulsion is necessary for this rotation to commence, and it is believed that supernovas, the final explosion of stars, could provide this as they generate shockwaves in space. As this disk rotates, matter tends to concentrate faster and faster towards the center, and it increases, absorbing more and more matter. When this mass reaches a critical point, where the pressure at the core is sufficient to trigger fusion, it transforms into a star. Typically, this new star undergoes a brief period of growth, during which it absorbs most of the disk's matter. In the instance of our solar system, the star consumed more than 99% of the total matter. We know that there are systems with several stars, 2 or 3 of varying sizes, highlighting that diverse models of aggregation are possible. But the single star model, like our system, is the most common. In any case, while this leaves little matter available, there is typically still enough to form several planets, which absorb the remaining matter from the protoplanetary disk, what the star hasn't engulfed. This protoplanetary or accretion disk forms the basis of planetary formation models. Nevertheless, theories explaining the specifics of planetary formation vary, especially for ice giants. Their existence posed a significant challenge to existing theories when their composition was discovered. The formation of rocky planets like Earth and gas giants like Jupiter is not very controversial. They are widely understood to have formed through millions of years of collisions of smaller rocky bodies within the protoplanetary disk, until one larger planet remains on its orbit, having cleaned up the orbit of all other bodies. But why do some planets become gas giants instead of terrestrial planets? The reason seems to be that these would have formed larger solid cores at approximately 10 times the Earth's mass. Consequently, with a stronger gravitational pull, they would also accumulate through accretion an envelope of gas. Observations within our solar system suggest that rocky planets are closer to the star, while gas giants are further away. This led to the supposition that the distance from the star helps retain gas. So, for a long time, it was believed that gas giants had to form relatively far from the star, from the center of the system, whereas rocky planets could occupy more central positions. Though they could theoretically exist throughout a large part of the protoplanetary disk, they would tend to become satellites or moons of gas giants if in close proximity to their orbits. But in the last 2 or 3 decades, this theory or assumption has been challenged by numerous observations made outside our solar system. With an abundance of exoplanets found in other star systems, it has been seen that there can be large gas giants or exoplanets orbiting close to their star, with very short orbital periods. In other words, they complete their orbits much more quickly around the star, taking only a few days compared with a year for Earth or 12 years for Jupiter. The discovery of these gas giants close to their stars led them to being referred to as hot Jupiters, named for their proximity to the star. Undoubtedly, their existence presented a challenge to existing theories about gas giants. These planets were the easiest to discover due to their size and closeness to their stars, resulting in a significant number of hot Jupiter discoveries. Consequently, the theories were revisited. Currently, the prevalent understanding is that hot Jupiters probably form far away from their star, then migrate closer to it. The migration could be gradual due to an imbalance in the system, until they find stable orbits closer to the star, or it could occur due to a collision, causing a sudden change in their trajectory in space. An alternative hypothesis is that they form in situ, close to the star, possibly due to a particularly large solid core that exhibits significant gravitational pull. The truth is that this remains an open question at this point. But returning to ice giants, when it comes to the formation of ice giants, existing models, though effective for explaining terrestrial planets or giants like Jupiter, struggle with deciphering the formation of these large planets located so far from the star. Why is that? Accretion of a rocky core requires collisions, plenty of them. For the formation of a protoplanet to occur, which progressively clears its orbit by absorbing everything within it. So, at the start, the protoplanets are rather small. A theoretical issue here is that, given their distance from the star, a protoplanet forming in the orbits of Uranus or Neptune should have been expelled when they were smaller in the solar system, following the laws of gravitation. It makes sense that planets like Jupiter or Saturn remain within the system. They are at 5 and 9.5 astronomical units from the star, respectively. The farther you are from the Sun, the less you are bound to the system by gravitation. The force diminishes with distance. At 20 units, like Uranus, or even more at 30 like Neptune, combined with the accelerating effects of Jupiter and Saturn, the protoplanets would have exceeded the escape velocity. In other words, they would have traveled fast enough in space to overcome the Sun's gravitational pull, and should have ventured beyond the solar system, or been absorbed by Jupiter and Saturn, or transformed into comets before fully forming. However, they evidently did not, because they exist. Yet the existence of a planet that formed via collision at 20 or more astronomical units from the Sun and remaining on a stable orbit is something current formation models struggle to explain. To further complicate matters, it seems that Uranus and Neptune are not the only exceptions. Many exoplanets discovered in other systems are strong candidates to be ice giants. So what could have occurred? A possible first scenario is that they might have migrated after their formation, much like the suspected behavior of hot Jupiters. These planets could have begun to form somewhere between the orbits of Jupiter and Saturn, 5 to 10 astronomical units from the Sun, and then altered their orbit at a time when their size and speed were sufficient to keep them bound to the solar system. It is not precisely explained how. There are various theories about this outward migration. For instance, it might have been due to close encounters with Jupiter or Saturn, which would have expelled them to another orbit. Another possibility is that they formed differently, near their current orbit, but in that case, it couldn't have been through collisions. An alternative that could work theoretically would be that the ice giants formed due to instability in parts of the protoplanetary disk. There could have existed regions of slightly higher density in the disk, which could have led to the formation of clumps of matter. These clumps would eventually collapse due to gravitational forces, forming a planet. Models suggest that a disk with a bit of instability could yield protoplanets between 10 and 30 astronomical units from the star, and both ice giants of the solar system are within this range. At this point, the formation of Uranus and Neptune is explainable. The thing we don't know is the specific mechanism of process, for those processes may have been very different. As we approach Uranus, now 19 astronomical units from the Sun, we see that although it is much smaller than Jupiter and Saturn, it was still observable from Earth centuries ago, perhaps as early as antiquity. However, for a long time, it was mistaken for a star or a comet. It wasn't until the late 18th century that several astronomers, noting that due to its movement, they realized it couldn't be a star and had to be a planet beyond Saturn. Uranus is about 19 times farther from the Sun than Earth, as we said, and has also slower orbital pace, so it takes much more, 84 years, to complete one revolution. Actually, since its identification as a planet in 1781, it has completed fewer than 3 full orbits. And also, as I mentioned earlier, we should note that it receives much less sunlight than Earth due to its distance. The intensity of sunlight varies inversely with the square of distance, meaning it decreases faster and faster as you move away from the Sun. Consequently, at around 19 or 20 astronomical units, depending on where the planet is on its elliptical orbit, Uranus receives 400 times less light than Earth. In other words, Uranus travels through space in the dark. If we look at the Sun from Uranus, it would appear as a small point in the distance, not the large, bright light that we see from Earth during daytime. Uranus has many moons. 27 have been identified to date. We will explore the largest of them, Titania. But before we do this, let's start our journey from the planet's atmosphere and travel inward to its core. Now, what we call the atmosphere is merely a gaseous envelope, since there is no well-defined solid surface on Uranus. The atmosphere has been identified as the region accessible to remote sensing, up to 100 bars of pressure. This covers a region that is still hundreds of kilometers or miles within the planet. We saw earlier that the pictures taken from Voyager 2 or lower definition telescopes suggested a peaceful, quiet, and featureless planet, which appears as a pale blue-green. This coloration results from the composition of the atmosphere, which absorbs red light. However, this impression may be misleading. In truth, the planet's atmosphere is quite active. For short periods of time, such as the 2 months in 2004, large clouds can form in the atmosphere, accompanied by spectacular storms. Record-breaking winds at over 500 miles per hour, or more than 800 kilometers per hour, have been observed. Though the climate isn't perfectly understood, it seems to be subject to significant variations. Since the 1990s, and thanks to advanced imaging techniques and different types of light, have revealed many clouds and atmospheric phenomena. The atmosphere mainly comprises hydrogen and helium, which account for an estimated 20% of the planet's mass. These elements are believed to be absent from the denser parts of the planet. The third element that makes up a bit more than 2% of the atmosphere is methane. The aquamarine color of the planet in visible light is probably due to methane. This atmosphere is intensely cold. Temperatures fluctuate based on altitude, but the coldest part regions of the troposphere, that is to say, the lowest and densest part of the atmosphere, they can reach near 50 Kelvin, below minus 200 degrees Celsius, or below 350 degrees Fahrenheit. The atmosphere on Uranus is less well known than that on Earth, but it's established that in the troposphere there are different layers of clouds where the pressure is lower. They appear to be made of ammonia, hydrogen, and sulfur. However, at higher pressure points, these clouds could be composed of water. These different levels of the troposphere have a highly complex and dynamic structure, with strong winds and seasonal variations. Below the troposphere, density and temperature increase, and progressively, hydrogen and helium diminish. And we come closer to a kind of mantle composed of ices that give their names to this type of planet. Although these ices aren't truly solid, they were probably solid before the planet formed. These compounds are referred to as ices because they would solidify if they existed in open space, as on a comet, or on the surface of a rocky planet. This mantle represents the majority of the planet's mass. In total, Uranus's mass is more than 1.5 times that of Earth. The gaseous envelope of the planet, despite occupying a lot of space, is intense. The mantle, which is denser, amounts to more than 13 Earth masses, or about 90% of the whole planet. Given the conditions, the main components, which are thought to be water and ammonia, are thought to be in a state of dense and hot fluid. This fluid state is sometimes referred to as water-ammonia ocean. By the way, you know what water is, but what is ammonia exactly? When hydrogen forms molecules with oxygen, you get water, as you know. Ammonia is a molecule that hydrogen forms with nitrogen and is abundant in the solar system. There is some on Earth, but it can be found in much higher quantities on Mars, Jupiter, Saturn, and, of course, Uranus and Neptune, where it is an important component. While it is found only in trace amounts in nature, on Earth, and is often associated in salts with other elements like chloride or sulfur, it plays a critical role in the cycle of life on our planet. It is a common byproduct of aquatic organisms' feeding processes and contributes to the nutritional needs of terrestrial organisms. Plants need it to grow, and it serves as a precursor to almost half of the world's food. Typically, fertilizers contain some. Returning to space, the mixture of water and ammonia, notable for its low freezing point, 173 Kelvin, which is minus 100 degrees Celsius, or 100 degrees less than water alone, could act as an antifreeze in other environments and facilitate the existence of liquid internal oceans at temperatures far lower than would be possible with water alone. However, it isn't a concern for Uranus, as a temperature where this water-ammonia mixture exists on the planet is estimated to be much higher. Where the mantle begins, the temperature hovers around 47 degrees Celsius, with a pressure of 100 bar, meaning 100 times the atmospheric pressure at sea level on Earth. Farther inside the mantle, both temperatures and pressure continually increase, reaching extremes at the center of the planet at an estimated 8 million bars and a temperature of approximately 5,000 degrees. A hypothesis suggests that within the mantle, methane, which is also present, could be broken up. Methane is comprised of hydrogen and carbon. Therefore, pure carbon atoms could potentially condense into diamond crystals that rain through the mantle, in a manner akin to stone sinking in a lake. However, this isn't a lake of water, but rather a mixture of water and ammonia under very high temperatures and pressures, superior to those in the deepest abyss on Earth. These diamond rainfalls may not exist solely on Uranus. Theoretically, they could also occur within Jupiter, Saturn, or Neptune. Another hypothesis is that there may be an ocean of liquid carbon at the base of the mantle, where the core begins. In this state, it is termed metallic carbon, due to its electric conductivity. Yet another curiosity would be the presence of water at such high temperatures and pressures that it transforms into something called superionic water, or superionic ice. This refers to a state where conditions are so extreme, unattainable on Earth, that water molecules break apart and oxygen crystallizes. That is to say, it adopts a highly organized, repetitive structure resembling a lattice. In between this lattice, hydrogen can float freely. This phase of water existed only theoretically until it was successfully synthesized in a laboratory very recently, in 2019. During the experiment, water was squeezed between two diamond pieces and maintained at very high pressure. It was then blasted by a pulse of laser, creating a pressure of 1,000,000 times greater than atmospheric pressure. It's staggering to conceive of, but the pressure inside Uranus could theoretically reach up to 8 million atmospheres, as we said earlier. So it is possible in natural conditions on this planet. The water was heated almost instantly with the laser to several thousand degrees, recreating the conditions believed to exist within the mantle of Uranus and Neptune also. As expected, the oxygen and hydrogen in water molecules broke apart, and the oxygen crystallized. This phase of water is also termed ice 18. In a previous discussion about the moons of Jupiter, we contemplated the various types of water ice that might exist under different conditions. Ice 18 is one more, and it may exist in a stable state in the depths of ice giants, even though we are unable to go there to sample and verify this hypothesis currently. After the mantle, the last part of the internal structure is the core. It is around this core that ice and gases aggregated during the formative process, or to where heavier elements possibly migrated. This is not entirely known, as I previously mentioned when discussing the planet's formation history. The core is believed to be relatively small, roughly half the mass of Earth, and is likely composed of silicate rocks, that is, silicon and oxygen, in addition to various metals. Now that we have quickly seen the inside, let's take a look at the periphery of the planet because there are more things to see there. First, there are rings. They are not very visible and generally not represented on views of the planet, but 13 of them are known. The majority of them are very narrow, only a few kilometers or a few miles wide, and they are made of very dark particles. These particles vary in size from microscopic to 1 or 2 feet. It is believed that these rings are younger than the planet itself. Some theories suggest that one or several moons may have been shattered by impacts and left their matter in orbit around the planet. With Uranus, we know it hosts a respectable number of moons. There are 27 of them. So let's focus on the largest one, Titania, which is also the 8th largest moon in the solar system. It is believed to have formed, much like the other moons of Uranus, from a small accretion disk that surrounded the protoplanet during the early stages of the solar system. In its composition, Titania is very similar to several moons of Jupiter that we visited during one of our space journeys. It has rock in the center and an exterior envelope of water. It's unknown whether some of this water could be liquid under a crust of solid ice. Titania is relatively small, much smaller than the Earth's moon, and it may not have retained enough internal heat to support underground oceans, subsurface oceans, like those suspected to exist on Europa or Ganymede. On the surface of Titania, there are abundant canyons. These aren't features that could be created by asteroid impacts. Canyons can form due to plate tectonics, but Titania is too small for that, or they could be caused by erosion. Yet Titania doesn't really have an atmosphere where meteorological events that would provoke erosion. So a hypothesis is that long ago, there may have been a liquid ocean on Titania's surface, under a layer of ice. It may have remained liquid thanks to the presence of ammonia. As we said before, ammonia, when mixed with water, is a powerful antifreeze because it freezes 100 degrees Celsius below water alone. Then, as Titania cooled down, this subsurface ocean would have frozen, making its volume increase. Such a process could have created surface canyons, as it would have broken the hard ice crust. Overall, Titania is an icy desert. It doesn't generate much internal heat, there is no atmosphere to retain the heat, and it receives minimal sunlight due to the distance from the sun. Nevertheless, there are still temperature variations due to seasons which are extremely long, due to a unique characteristic of Uranus. Uranus has the unusual trait of presenting its pole to the sun rather than its equator like other planets. This is thought to be the result of a major collision in the past that would have tilted the planet. The moons orbit around the equator of the planet, and Titania always presents the same face to Uranus because it is tidally locked to it. This means, in terms of seasons, is that when Uranus is on one side of the sun, Titania presents one of its poles to the sun, and when Uranus orbits to the other side, the opposing pole is exposed. Furthermore, given that Uranus takes 84 years to complete one orbit around the sun, this means the seasons on Titania last 42 years. One side is bathed in light for 42 years, whereas the other half remains dark. After this period, they switch for another 42 years. Now, let's continue our journey and move to our second destination, even farther away from Earth. Uranus is about 20 astronomical units from the Sun. To reach the orbit of Neptune, we need to travel 10 more astronomical units. Neptune, as we're about to see, is near a twin of Uranus, but with a few differences. Neptune is so far away that it is invisible from Earth to the unaided eye. This is why it was the first planet discovered not by observation, but by mathematical prediction. This happened in the first half of the 19th century. Uranus had been found and was observed by telescopes, and its orbit was mapped. However, something was off. There were unexpected changes in the orbits of Uranus that weren't really explainable by the existence of other planets and the laws of gravitation. So either there was something wrong with the calculations, or there existed yet another unknown planet that influenced the orbit of Uranus. The position of a possible eighth planet was deduced from the perturbation of Uranus's orbit, and this ghost planet was tracked in the night sky until 1846, when it was found. In the following decades, several moons were found around Neptune, starting with by far the largest one, Triton. We'll take a look at it a bit later. In terms of composition, structure, and size, Uranus and Neptune are thought to be very similar, with an envelope of hydrogen and helium, ice is inside, that is to say water, ammonia, and methane, to a lesser degree, carbon dioxide. But in visible light, Neptune looks bluer. This is believed to be due to more methane in the upper layers of the atmosphere and possibly another component that has not yet fully been identified. Another difference is that Neptune is a bit more massive than Uranus. It has 17 times the mass of Earth versus 14.5 times for Uranus. While it might sound counterintuitive, Neptune is also physically a bit smaller. This is due to its mass, which implies a bit more compression of its atmosphere. In balance, it has a bit more matter in a bit less space. Another difference is the distance to the Sun. The two planets are 10 astronomical units away from each other, a huge distance that is about the same as the distance from the Sun to Saturn. This means even less sunlight. Neptune, because of its larger mass, is internally a bit hotter. So the temperature at the center is estimated at 5,400 Kelvin versus 5,000 for Uranus. Despite this, its atmosphere is one of the coldest places in the solar system. The temperature approaches 50 Kelvin, which is below 200 degrees Celsius, and only 50 degrees above absolute zero. Since its discovery, Neptune has completed only one orbit around the Sun. It takes 165 years, twice the time Uranus needs. Yet another difference is the intensity of meteorological activity. Compared with Uranus, Neptune's atmosphere is far from peaceful. There are giant storms constantly, a complex system of clouds, with the most powerful winds in the entire solar system. They blow constantly at more than 1,000 miles per hour in the upper atmosphere. This is believed to be a consequence of the temperature differential between the core and the mantle, which are hotter than those of Uranus, and the atmosphere, which is cold in its upper parts. As you know, winds are produced of gas masses moving from one place to another due to a differential in pressure and temperature. And on Neptune, these differentials are bigger. And so the planet looks constantly agitated by giant storms that have been observed since we have been able to produce higher definition images. For a time, there was a big dark spot, comparable in nature to the great red spot on Jupiter, which is a storm. It eventually disappeared, but more perturbations are constantly appearing and disappearing on the surface. Beyond Neptune begins a region called the Kuiper Belt, a very large region of the outer solar system, teeming with millions of smaller asteroids. Pluto, the dwarf planet, is one of these bodies. The edges of the Kuiper Belt have been set from 30 astronomical units away from the Sun. That is to say, Neptune's orbit to 55 astronomical units, and Neptune strongly influences the Kuiper Belt due to its gravitational pull. It has shaped its structure over time, after hundreds of millions of years and millions of revolutions around the Sun. This is evident in the number of objects that are in orbital resonance with Neptune in the Kuiper Belt. I explained the concept about Jupiter's moons because 3 of them are in orbital resonance. To summarize, it occurs when 2 or more objects on different orbits become locked by their respective influences on each other, with their revolutions occurring in a stable ratio. In the example of Jupiter's moons, every time Ganymede completes 1 orbit, Europa completes 2, and Io completes 4. So they are set to be in a 1, 2, 4 resonance. Similarly, Neptune is in resonance with dozens of smaller bodies in the Kuiper Belt, starting with Pluto. They are in a 2, 3 resonance, which means when Pluto makes 2 revolutions, Neptune makes 3. Other ratios have been found with other bodies, such as 3-4, 3-5, 2-5, 4-3, 4-7. Over time, the Kuiper Belt has come under the strong influence of Neptune's mass and orbit, in a manner akin to the influence Jupiter has on the smaller asteroid belt lying between the orbits of Mars and Jupiter. Neptune also has 40 known moons, most of them small, except for one, Triton. Triton alone represents more than 99% of all objects orbiting Neptune. All other moons combined do not even comprise 1%. Therefore, let's focus on Triton because it possesses unique elements and aspects that distinguishes it from most moons. The first of these is its retrograde orbit, meaning it orbits in the opposite direction to Neptune's rotation. This is a very rare occurrence for large moons in the solar system. Most of the time, they follow the rotation of their planet, exhibiting prograde motion. This is a strong indication that Triton did not form in Neptune's periphery, but was captured later, possibly from the Kuiper Belt. Had it remained in the belt, it would have been considered a dwarf planet, similar to Pluto. Triton is slightly larger than Pluto and nearly as large as Earth's moon, making it quite sizable, in fact, the seventh largest moon in the solar system. Its surface appears to have been renewed, as suggested by the density of impact craters. There are few. This strongly indicates that if the moon can renew or rejuvenate its surface, it is geologically active. That is to say, it has a differentiated structure with a core, mantle, and crust that would be coherent with its size. Moreover, there seems to be two types of geological phenomena at the surface: cryovolcanism, meaning eruptions of warmer materials like water that surge and subsequently freeze on the surface, and tectonic activity, which releases other materials from inside the moon or allows plates of the crust to move. This is how mountains and drifts can appear. How can a body of such size be captured, bearing in mind the vast distances within the Kuiper Belt? Several possible mechanisms exist. Nonetheless, it likely required a very long time and perhaps millions of orbits around the Sun. Parts of Triton's orbit may have intersected or neared Neptune's. Neptune's gravitational pull could gradually have slowed Triton, reducing its speed below the escape velocity, allowing its capture by gravitation. This slowdown could also have resulted from the collision between Triton and an ancient Neptune moon now vanished. Alternatively, Triton could have formed a binary system with another body, like Pluto and its largest moon, Charon. Neptune's influence on this system could have led to an interaction that pushed Triton into an orbit around Neptune, with its partner expelled from the Kuiper Belt, or even possibly from the solar system altogether. We don't know. But it seems that Triton's arrival had catastrophic effects on Neptune's ancient moons. It disrupted their orbits, potentially causing collisions, and the gravitational interactions could have scattered smaller moons when the system stabilized. Triton constituted more than 99% of the mass orbiting Neptune, the rest being faint rings and small irregular moons. At the surface, Triton is enveloped in a layer of frozen nitrogen. In this region of intense cold, it may also hold a water envelope accounting for 15% to a third of the moon's mass. Beneath that, a mantle and a core of rock and metal could be present. Like many moons we have visited in our stories, there might be liquid water, a subsurface ocean, that could theoretically harbor life. However, this is speculative, and it's already hard to imagine an expedition to Europa or Ganymede, which is 5 astronomical units away from the Sun. Triton is 6 times further at 30 astronomical units away. The idea of launching a manned expedition to explore it remains science fiction. At this point, it takes a lot of patience to send probes to these regions of our solar system. All space missions take time, but this is really far. You remember we talked about the probe Voyager 2, for instance, was the first NASA probe to capture nearby images from Uranus and Neptune. Launched in 1977, it reached Jupiter in 1979, then Saturn in 1981. And finally, after an additional 5 years and despite accelerating speeds, it reached Uranus in 1986. and still continuing to accelerate, it reached Neptune in 1989, 12 years after its launch. Voyager 2 remains active and is now on a mission to explore interstellar space, 44 years after departure. The distance Voyager 2 has traversed is absolutely mind-blowing. When it reached Neptune 32 years ago, it was at 30 astronomical units from the Sun. Then it traversed the entire length of the Kuiper Belt, which concludes at 55 astronomical units, eventually exiting the solar system's zone of influence at 120 astronomical units in 2018. Voyager 1, also built for interstellar exploration and launched almost at the same time, is still operational and currently is at more than 150 astronomical units from Earth. These two probes are by far the human man-made objects that have traveled the furthest ever. We have finished our full tour to the ice giants. If you wish to visit other space destinations, we have more stories in our library for your enjoyment. But for now, you can let go and fall asleep. And until we meet again, good night. Sleep well.